Uh, Hello, good morning, everyone. I want to welcome you to my lecture today. Of course, today I'm going to walk you through what we call the theory of convex functions. So why am I bringing this? I'm bringing this because this have connection with other topics we're going to be doing. For instance, on Wednesday, we're going to start clustering. And of course, you know, you need to be able to have the theories that guide convex functions for you to be able to understand that. And that's why I'm bringing this. Okay, so in the outline, I'm going to walk you through give you some examples of univariate and multivariate or convex functions. Then I'm also going to tell you that we got different kinds of convexity. We got straight and we got strong. Okay. Then I'm also going to walk you through what I call first and second order characterization of convex functions. Then we're going to have work examples on convex functions. Before you start, I'm going to say this. You need your knowledge of multivariable calculus here. Okay, from now. Okay, you can revise that knowledge. Okay, so once again, I want to welcome you to this class that I call the theory of functions, the theory of convex functions. Okay, and of course, I've already said, mentioned about what the outline is going to be. So let's get started. Of course, you know, in any optimization problem, of course, it's either we're looking for, you know, the, the global minimum or the global maximum, depending on the type of optimization. Okay. Um, but by the moment, we just want to be focusing on, minimizing a function. Of course, I told you what is required. The nature of function is very important. Okay. Uh, it has to be convex function. Okay. It has to be convex function. And of course, this is what we mean, by a convex function. Okay. We're mapping, a real number and dimensional into another real number. And of course, if the domain is a convex set, for X and Y in the domain, where we got a weight, this is a weight parameter, it's always going to be between 0 and 1. So if we can actually have this, okay, if I have, this guy or she, okay, is actually the line, this particular, a point on this line, okay, a point on this line. So a point on this line, when you're trying to evaluate the function, it should be less, okay, or equal to the weighted function of X and Y. That's exactly what we mean. Okay. So this is whenever that happen, that implies a convex function. Okay. So this is a picture for that. Okay. Now, the next thing that I actually, what I want to talk about now, is, we got different kind of convex function. Okay. Convex can be strictly convex and can be what I call strongly, convex. Okay. So what you are seeing, right now is actually, the condition under which a particular function, okay, can actually be classified, okay, to be either strictly convex or strong or strongly convex. Okay, now I need you to pay attention to this again. We actually have a function that is mapping. And of course, if I can take X and Y in, in that domain where S is not the same, as Y, okay, then if the function of that particular line that I said the other time, okay, on the segment, okay, if it is strictly less than the weighted function, okay, we're actually going to call that strictly converse. But situation whereby there exists an alpha, such a way that the alpha is positive greater than 0. Okay, if I can have f of s minus alpha multiplied by the square of norm, then I'm actually going to call that a strongly converse. Okay, so let me tell you this. Strictly converse and strongly converse functions are both important concepts in optimization. Okay, especially when you are trying to determine the uniqueness and stability of a solution. Okay, so I just wanted to take note of that. But let me tell you this: when you want to focus, if you take a look at it strictly uh converse, okay, for strictly converse, you can guarantee a global minimum. Okay, with strictly converse, there's no local minimum at all. Okay, in the strictly converse, there's no local minimum at all. Okay, now and another thing is there's nothing like a flat region. Okay, no flat region. Okay, you know, so the functions do not have any flat region that curve upward. Okay, everywhere within the domain. That is what we mean by strictly converse. Okay, but when you want to talk about, the strongly converse, at the other hand, okay, of course, that also guarantee a unique global minimum, okay, like strictly converse function, okay. It also have a unique minimum. Of course, that's a sharper curvature, and of course, the strong convexity also guarantee that all function is well conditioned for optimization. Okay, now what is the difference? Okay, between the two, which I'm actually going to point out right now. Okay, for strictly convex functions, okay, it has some degree of curvature everywhere, but not require a lower bound. But for strongly convex functions, of course, they are strictly convex with an additional condition, okay, that ensure the function is quadratically curved. And that was why, we're introducing this. Okay. Okay. Now, I'm actually showing you examples of univariate or converse function right now. Okay, you got you're working on a variable x, and of course you're trying to figure out what kind of functions you want to look at the nature function that can guarantee convexity. Okay, so exponential raised to the power s, the minus log s, all of these, they are very, they are verifiable univariate you know converse functions. Okay, I just wanted to take note of that. Okay, now and you can also verify that, you can verify then, on your own, for you to be able to see. Now I want to go into a layman now. Okay, I actually, for us to be able to distinguish mathematically between strong convexity and straight convexity. Okay, I actually want to demonstrate right now. Okay, the fact that straight convexity implies complexity, that is actually obvious. Of course, what I'm trying to say, for this, that's apply that's actually guarantee this actually is strictly because it's strictly converse, or we actually are going to say that is that's attain convexity. Okay, But in the strongly convex, we have to impose a condition. Okay, you can see what we're bringing in. Okay, now if you take a look at what I have, okay, if you take a look at what I have right now, okay, take a look at what I have right now. Okay, now if you look at what I'm trying to do here, okay, it's like inside inside the strongly convex. Okay, you know, I have f of s, like I want to put the whole of this, I want to put the line on the straight line. Okay, I want to put the point on the line segment into that. Okay, wherever I have x here, I want to put the whole of this. Okay, I also want to do that here. So take a look at that. That is exactly what I'm doing here. You can see that now. So I've already plugged in that here. Okay, you can see what you have here before was just x but replaced by this. Okay, and of course that is less or equal. If you take a look at this side, that's a weighted function. Okay, and this is when you incorporate the norm square. So it's more or less like you are having this side, you know, talking about the f of s, and and this is the version of the norm. Okay, that is the version of the norm. So that is exactly what we're trying to talk about, and we can verify, you know, that this guy is going to be greater than 0. And if that happens, then we can actually conclude. So you can actually you can try this guy out. Okay, you can try this. For instance, if f of s is a convex, okay, but not strictly convex, and f of s raised to the power 4 is strictly convex. So how can you verify that, even though this is a convex, but it's not a strictly convex, because it also has a tendency, okay, to be a concave. Okay, so you can investigate that. Then also for this guy, okay, you can even, you know, when you investigate this guy, you're actually going to have equality, which can go either way. That's not strictly convex. But if you investigate this guy, okay, the condition of strictly convex is going to hold. The condition of less or equal is actually going to hold. You can try that. Okay. Now, the next thing I want to talk about, you know, if I want to investigate whether a function is a convex, right? I can go by way of drawing graph. Okay. I can use theoretical approach here. Okay, I can use this, provided if this is less than that, that's a strictly convex. And if this guy hold, that will be a strongly convex. Okay, so that I make use of this. Or another way I can investigate that is to make use of the first and the second order characterization of convex function. But before I can do that, I got to make sure that you know, the functions is twice differentiable, okay, over an open domain. Okay, so number one, f is a convex, and we can have a function of y that will be, you know, given situation where s is not equal to y, right? Okay, the f of y is expected to be greater than f of s by this margin. And what do you see in this margin? That's a derivative of f of x. Okay, that is more or less like a first order characterization. Now, the second order characterization is actually this. When I differentiate the function twice, okay, that must give me non-negative. Okay, in case you are using gradients, okay, if you're using gradients, if you obtain your Asian matrix, the diagonal of the Asian matrix, which are the eigenvalues, if they are all positive, okay, if they are all positive, of course, that will be a positive definite. The positive definite actually implies straight convexity. Okay. But you can also have situation whereby it's a combination of positive and zero, and that would be semi-positive definite. Okay. So semi-positive definite, okay, there's possibility that uh one is likely going to run into what I call saddle points, which I'm still going to talk about. Okay. A situation where uh this is less than zero, which means negative, which means the second derivative, which occupy the diagonal of the Asian matrix, is negative. That is not a converse at all. Okay. That is not a converse at all. Okay. So you're going to understand this by the time I get to gradients, okay, in optimization. Okay. So we can guarantee, okay, here I said the first order Taylor expansion at any point is a global underestimator of the function. Okay. It's actually going to be global if this guy hold. Okay. And of course, if you take a look at the other guy, and this is the reason why it's going to be global, because you know, the plane is actually the curve of the function is actually going to be on top of that. Take a look at that. So if you take a look at this guy now, you're actually referring to the f of you can see that the f of y now, which is a function, is greater than the line. The point on the line, like I said the other time, this line now is this guy. Okay, and that was what I was trying to say here, that this guy is greater or equal to that. Okay, now this guy here that is talking about the second derivative has to be non-negative, is that we guarantee a non-negative curvature, because that is what is needed, as you can see here. Okay, now I'm going to go into examples of multivariate converse function. For multivariate converse function, particularly if you have this quadratic, okay, where Q here, okay, may necessarily be it may be let's say like a quadratic functions, that should be greater or equal to zero. For strictly converse, has to be greater than zero. It's like trying to talk about it, like in the Asian matrix, the diagonal has to be, all values, they have to be positive. That is strictly converse, right? That guarantee global minimum. And of course, can be converse are not strictly converse if it is greater or equal to zero, which means some numbers in diagonal can be positive and some can be zero. That's a semi-positive definite. Why this is a positive definite. But the tragedy is when it is less than zero, when you have negative, that's again going to be concave. And also to tell you any norm, like this, where f satisfy that, and where f of s plus y can be less or equal to that, and where f of s greater than or equal to zero, and that, for s equal to zero, of course, all of that satisfy the converse. Okay, so another thing is to tell you that when you see a function like this, A transpose x plus b, okay, we call this an affine functions. Okay, an affine function can actually be a converse. They are not strictly converse. So the moment a function is not strictly converse, then it can also be a concave. Don't forget, concave is not good for minimization problem. So if I really want to know, okay, I can actually go back to the definition of a converse, the definition here. If you take a look at this definition now, okay, now I want to apply, this is for a function x, right? Now, if I want to go for a function, A transpose S plus B, so which will mean this guy, I actually want to plug it here. I also want to plug it here. Okay, so when I plug this guy here, okay, it's going to lead to this when I simplify. Okay, if I plug it here and I simplify, I'm actually going to have this guy. Okay, and if I simplify further, where I introduce here introducing a lambda b, and here I can have a negative lambda b that can cancel out, and b, this one. So what I'm trying to say, this guy is the same thing as that. Okay, you just introduce lambda b, and that's something that can make it, we're going to go to b. But the essence of doing that is we actually want to have a way to curate the weight. Okay, now if you take a look at this now, I can factorize. Okay, I can actually factorize. Okay, if I can bring this guy, right, and this guy, they both have lambda. Okay, which is going to be lambda f of x. Okay, and this guy and this guy, so this is that, then this guy. Okay, you can see now. Okay, and plus b, so it's going to be f of y. So you can see now that's directly equal to that. When it is directly equal, then it means it is convex, but not strictly convex. It can also be concave. So equality implies it can be either convex or concave. And that was why I said the affine functions are the only function that are both convex and concave. Okay, I just wanted to get that as information. So far so good, right? Okay. Now this just to show you pictures, for an affine function, for quadratic function, for one norm. If you take a look at that, you can see curve here, right? But here, this is an affine function. It can be a concave, it can be a convex. It's not strictly convex. Okay? Okay. Now I want to walk you through work example now. Okay, for instance, I know that this is a definition for convex, right? Okay, don't forget when I have less than, okay, that will be strictly convex. Okay, when I have equality, so that may mean that it's a convex, it can also be a concave. Now, uh, what if I ask you to say which of the following functions are convex? I give you absolute value of x, the cos of x, and the s squared. There are several ways you can look at that. You can draw a picture to see for yourself, to see whether you have a curve. Okay, you can draw a picture. Okay, we can do other things. We can use this formula to investigate. Okay, now if this is acting like an f of x, then I want to get f of absolute value of x. Take a look at what I'm going to do. Okay, so f of that now, okay, I'm just going to, you can see here, absolute value of x. I'm going to do absolute value of that point, which is what I'm doing here. Look at that. You see the absolute value of that now, right? Okay, and this guy here, okay, if you look at it, the law of inequality with absolute value, okay, where you have absolute value of x plus y in mathematics, okay, that could be less or equal to the absolute value of x, okay, plus the absolute value of y, okay. Now we can apply the same here. Okay, so lambda is a constant. I can just, okay, this is going to be less than lambda that plus that. Okay, so which confirm this to be a convex. Okay, you can do the same thing for s squared. Okay, what I'm just going to do is to square this particular guy, which is what I'm doing here. And when I square that, I'm going to let it to be less or equal to, okay, the lambda s squared, because don't forget we have lambda in the formula, lambda, okay, and f of x, right? Lambda f of x, okay, and don't forget we have 1 minus lambda, okay, 1 minus lambda, and this guy is going to be f of y. You remember the weighted function, right? So all what we're going to do now is to simplify and solve that and be able to establish that this is going to be less or equal to 0, because if this is less or equal to that, if you simplify, if that's going to be less or equal to 0, of course we can say we've proved that. Okay, so far so good, right? Okay, now the next thing that I actually want to talk about, and when you investigate cos x, because it's an oscillatory function, okay, it's never going to be a converse. An oscillatory function can be a converse. I just wanted to take note of that. Okay, so converse functions are useful because local minima are always global minima. I told you. Okay, every local minimum is a global minimum when you are using converse function. And how is that true? Okay, now the reason why suppose you want to go by way of contradiction, and you said let's say S is a local minimum but not a global minimum. Okay, you want to go by way of contradiction, and since the function is converse, now we need to draw a line segment between X and the global minimum, if this is the global minimum that we talk about, and an X. Okay, now the segment should be going down as it leaves the X. Okay, so and I said YF should be going up. You can see now this is F. Okay, should be going up. Okay, so going up in every direction from X. Okay, so since X is a minimum, then we can say the line segment is going down while F is going up. Okay, and the segment has to go below F. That's a contradiction, right? Okay, which contradicting convexity. And that is the reason why it is not possible when you are working with a converse function for a local minimum not to be a global minimum. That's exactly what we established. Okay, so of course, since we've defined a converse function, then if I switch the sign, instead of less or equal, I change it to greater. Of course, that will be a concave, no longer a converse. And I also wanted to take note that if f of s is a concave, if I multiply it by -1, it's going to be a converse. And if f of s is a convex, if I multiply it by -1, it's going to be a concave. An example is a log of x. If you take a look at the logarithm of x, okay, the logarithm of s is actually concave. If you multiply it by -1, it's actually going to be convex. You can try that out. Okay, and this is a proof. Okay, you know, the only thing is just for you to from here, okay, multiply both sides by -1. That will change the sign less or equal to be greater or equal. That's a simple one. That's very simple to show. Okay, this is the converse, this is concave. Okay, now so far so good. Okay, now in exercise 4, can a function be both convex and concave on the same set? Okay, then I'm going to say yes, and I give example of linear function the other time. Okay, linear functions, they are both convex and concave because of the sign of equality. Look at that, equality. So anytime you have a sign of equality, they could be concave, they could be convex. When you have less than is strictly convex. Greater than is concave. Okay. Now, if I want to go by, I'm not, maybe I'm not interested in drawing a function, I'm not interested in drawing a graph. I'm not also interested in using that theoretical formula that I showed you the other time. But I want to use second order condition to verify convexity. I can only use that if my function is twice differentiable. Now, what I'm going to do is, um, if I differentiate my function twice and it is greater than 0, okay, I'm actually going to say convexity condition reached. For instance, let us show a negative log of x is convex. So what I'm going to do, forget this log is a natural log. If I differentiate first time, I got it. Second time, you can see no negative. So for s greater than 0, of course, that is going to be positive all the time. Okay, and because of that, I'm actually going to say negative log s is convex. You can also plot that for you to be able to see that is naturally convex. Okay, if you do that to the positive log s, you're actually going to see in the end, the second derivative is actually going to be negative. Okay, now use the fact that the negative log s is convex to show the arithmetical mean geometric mean inequality. Okay, for a big or greater or equal to 0. So if you take a look at this side, that's a geometric mean. If I have two observations, geometric mean is just the square root of the two observations. If you have n observation, it's going to be n roots. And of course, we all know arithmetic mean to be adding together and divide by the number. So if I want to start, I just need to know that log is monotonically increasing. So if I introduce log AB divided by 2, for instance, log AB, okay. Now, why am I, because if you introduce a log here, okay, it's going to be log, okay, log square root of AB, right? Which is the same thing as, log, okay, which is the same thing as log A, B, all raised to power half, right? Okay, and you can rewrite that as bringing half down and just have log, okay, AB. So which is what you have here, okay? So you're trying to introduce log to that, okay? Now, log of a product. So this guy is still this guy. Now, introducing log to this side, of course, you have this side, right? And take a look at that. Now, the next thing that we actually going to do now is to simplify that. So I got log A plus log B divided by 2 less or equal to that. Okay, now if I have this guy now, what I can do is to multiply by -1 because it's asking me to use a fact that the negative log of x, because if I don't multiply by -1, that may not hold. And don't forget, the negative log of x is a convex, as we proved that before. So multiply both sides by negative, okay, we actually gonna have what we have right now. We're gonna have that, and of course, if you rearrange that, we actually flip the inequality that we talk about. Okay, now the next thing that I want to do now, going into exercise 7, show that if f is convex, then g of s equal to f of a s plus b. Okay, so we want to make use of the definition of convexity. Okay, now what we're going to do is wherever we see x, what we plug in the other time. Okay, if you take a look at this guy, okay, I'm actually plugging in the whole of that as plus b. Okay, now when I plug in the as plus b into that and I factorize and I simplify, I'm actually going to have this guy. And the moment I have this guy, I actually want lambda to be in one side and 1 minus lambda to be in another side. Okay, I'm going to have this. So which this is like talking about f of x or the g of x, and this is talking about g of y because the g of x equal to that. And at the end of the day, if you take a look at that, what we are having now is that we've been able to show that is convex. Okay, I want to go into gradients now. Okay, I'm going to say this in mathematics, or specifically in multivariable calculus. The gradient is a vector that contains the partial derivative of a scalar function. Okay, so and that is very, very useful in optimization algorithm. Okay, because it's actually going to point in the direction of the greatest rate of increase, okay, of the function and its magnitude corresponding to steepness of the function at that point. Okay, so if that happen right now, we actually want to examine the gradient, the gradient descent algorithm and study the effect of a learning rate alpha on the convergence of the algorithm. Remember the other time I walk you through, giving you, this, okay, to be the iterative form that is actually going to be. So when you take a look at this, like st plus 1 is the s new, this is s old, and the alpha is the learning rate, okay, and delta f is actually going to be the first derivative, okay, it's going to be the first derivative of the function. Now, what do I want to do now? Suppose we want to minimize this guy, okay, want to minimize the function, okay, then we run the gradient descent by hand, okay, to compute using when alpha equal to 0.5, when alpha equal to 0.1, when alpha equal to 10, because we actually want to test different learning rates to be able to see which one we should pick. The one that we're going to pick is the one that converges faster compared to the rest. Okay, so I'm going to show you, the process right now, but we have an observation that when alpha equal to 0.5, okay, the algorithm will reach the minimum at which reach the minimum at one step. When alpha equal to 0.1, the algorithm eventually converges, but could take forever at times. And for alpha equal to 10, we are overshooting, okay, which means the algorithm is not going to converge. Instead of converging, it's going to diverge, and that's not going to be good at all. Okay, so I want to demonstrate right now. I want to start the process with alpha equal to 0.1. Okay, alpha equal to 0.1. What we're going to do, don't forget the iterative algorithm. Okay, we need to first take a look at this one. There are we need to differentiate, right? Differentiate this guy, we got this guy, right? Okay, so when we get this guy right now, okay, so what we're actually gonna do is we can start plugging in. Okay, we can start plugging in value. Don't forget alpha is gonna be 0.1. So if I start with x1 equal to 6, okay, it's good to start with x1 equal to 6. Why am I actually starting with s1 equal to 6? Maybe probably because the constant here 6, okay, maybe that's be a good way to, so we can start with s1 equal to 6. Okay, s1 equal to 6, you can see that right now. Okay, and at time we can make a suggestion about what your starting point is going to be. So if I want to do this one now, if I plug in 1, that would be x2, x1, don't forget your x1 is 6, alpha equal to that. Now I'm going to plug in, how do I get 8? Okay, how do I get 8? Okay, 2 times 6, okay, that would be 12 minus 4, that would be 8. So S2 now is going to be 5.2. I'm going to continue the process until it converges. Okay, it converges. Okay, just want to take a, but if you go by if you take alpha to be 0.5, it converges, but which is not always the case. You know, in fact, it is rare that this actually happen. And let me say, when alpha equal to 10, you are actually going to overshoot. Overshooting in the sense that the algorithm will cause you to move further away from the minimum, and that's not going to be good. That will diverge. We don't want that. So what we see now, the effect of the learning rate. We need to choose your learning rate wisely. Okay, so it's another example for two variable situation. Okay, like consider two variable function x and y. Okay, and starting from the point 2 and 3, you can say you're always going to be, they're going to give you that. So that is the starting. Then run the descent with a step size of 0.1. Now, in the case of this guy, um, we're actually going to perform derivative twice. Okay, so the df, okay, I'm actually we're going to have the first one, the f, okay, the partial derivative of the function with respect to x first, okay, and you're also going to have the partial derivative of the function with respect to y. Okay, now this guy, we got that when we differentiate this function with respect to x, and this guy when we differentiate, okay, with respect to y. Okay, you can see here the first derivative is a vector, and we're going to have the iterative function that we actually are going to have xt plus 1, okay, equal to st, okay, minus alpha, okay, and here is going to be the f dx. Okay, don't forget we are dealing with two variables situation. We're also going to do the same to y. So yt plus 1, okay, yt plus 1 equal, yt, okay, minus alpha, and this is going to be the f, okay, dy. Okay, so don't forget you're giving a starting point x1 equal to 2, that equal to 2. So here, if you plug in, if you want to find for x2 now, okay, that will be x2 equal to x1. Okay, you know what your x1 is 2 minus the alpha given. Then df ds, if you come to this one, okay, you plug in the values available. So you're gonna have ps of values at each step until it finally converge. It's gonna convert to that. Uh, this thing goes indefinitely, okay, until it converges. Okay, that is how that is done. Okay. Now, the next thing that I actually talk about now, okay, is to go into, we can give you functions and ask you to determine whether it is converse, strictly converse, or strongly converse, or none of the above. So you know how to go about that. Okay, so lastly, I'm going to tell you the essence of convexity inequality. Okay, so the convexity inequality, any local minimum, of course, going to be a global minimum. And of course, that will actually make solution, very very easy to find. Okay. Then algorithm efficiency, the convexity actually guarantee convergence optimization. Okay. You actually you're going to converge very fast, and you can be assured of that. Then it's actually the convexity simplify dealing with the constraint and feasible region. Imagine you're working with a linear programming where you state your objective function subject to constraints, and you're actually going to be looking for feasible region. Okay, so with convexity inequality, of course, the feasible region that you choose will behave well. Then the monotonicity of first order condition, okay, the gradient will always point in the direction of the steepest ascent. And we move in the opposite direction, guarantee a decrease in the function value. That's exactly what we want. Let me tell you this. The convexity highly applicable in machine learning and data science. Of course, when you in machine learning, of course, yeah, I don't know where you heard about loss function. They want to minimize loss function. Okay, and even in statistical analysis, where we may want to minimize the sum of square error. Okay, when we are seeking, explanatory goal. Okay, and of course, it will also the convexity inequality. We also help us to avoid overfitting. When you take a look at ridge lasso regression, particularly in the ridge regression where we introduce what we call the L2 regularization, that we impose a convex constraint on the model. Okay, that becomes necessary. Now, duality and a strong duality, in linear programming where you have a prima and a dual, of course, you know, that will guarantee that the quality gap, which is actually the difference between them, is zero under certain conditions. So talking about robustness, convex function actually provide what we call stable solutions. Okay, stable solution in the sense that when you change the output, it's not going to have effect on the output, even when the inputs are noisy. Okay, so now what are the reasons why we get trapped in the local minimum? Don't forget, local minimum is not that fine. Okay, it's like having a minimum within certain neighborhood and not having minimum globally. The reason being that maybe you are not using convex function, so you got to use convex function. And another reason maybe be using a gradient-based optimization algorithm. Okay, because at times the gradient-based optimization algorithm may actually fall into local minimum trap, and it actually need a speed or momentum to be able to get out of that. Okay, so we also need to use what I call a global technique in exploration so that we don't get trapped in local minimum. Then you got to make sure that your objective function is not noisy. Okay, you got to make sure it's not noisy. You're trying to actually scale things down. Okay, then the step size, they don't use a step size that will be too large or too small. You remember the other time when we're trying to minimize a function, when we use alpha equal to 0.1, 0.5 and 10, you saw what happens. Some converges, others diverge. Okay, now and like I said, algorithm can become stuck, okay, at a saddle point, okay, mistaking it for a local minimum. Okay, so it can get stuck. Okay, then dimensionality, for instance, you got so many variables, so many features. Okay, now when you have so many variables, it will be more challenging to exploit the entire space, leading to frequently trapping in local minimum. Okay, you may want to ask, how do we get out of the noisy one? Like if you have some variables that have different units, for instance, particularly in principal component analysis, what we normally do is to first standardize before we actually begin the analysis. Okay. Now, objective function poorly scaled. Okay. This is exactly what I'm trying to say. You got so many variables, they have different units. Okay. You need to scale them. Okay. Uh, this is where the idea of scaling come in. So the moment there's so many variables, maybe the unit is different, some in dollar, some in kilogram, don't forget we work with high dimension data at times where we collect data over so many variables. Okay, so objective function that is poorly scaled. Okay, let me tell you this: if the function is convex and it is poorly scaled, that doesn't mean that it's still not going to achieve global minimum, but it's going to struggle. Okay, it's going to struggle. They're all going to struggle. So that is what I mean. Okay, so the strategy for avoiding local minimum in optimization is random restarts. And this is the reason why in clustering, okay, we normally run the optimization algorithm multiple times with different initial point before we could arrive at the optimal numbers of clusters. Of course, on Wednesday, we're going to start clustering. And of course, you're going to see us doing that. Okay, so simulated annealing, we're talking about we got some method, that allow the algorithm to escape local minimum in their early stages of the optimization process. Now we need to use a global optimization algorithm like genetic algorithm or particle swarm. Okay. They are designed to search the entire domain broadly. Don't use algorithm that can only search within locality. Okay, within locality. We don't want that because you may end up with local minimum when you search within locality. So you got to use a global optimization algorithm that will allow you to search everywhere. Okay. Okay, so momentum gradient descent. I told you the other time, when it is slow, okay, it could get stuck. So all we need to do is to add momentum to the gradient descent, and that will allow the algorithm to keep moving, even when the gradients are small. Helping you to escape local minimum. So when it gets stuck, the moment that momentum will keep it going, so it's going to pick itself up. So what is next? Of course, on Wednesday, I'm actually going to introduce this class to clustering in machine learning. So is there any question before I go today? Okay, so make sure you all stay safe and have a lovely day. See you on Wednesday. Bye for now, everyone.